Okay, so let's get going on talking about secondary compression now. I'd like to start just by talking about the definition of secondary compression, which seems like a really basic thing, but there is some sort of subtlety there in how we define it. So the basic idea is that after excess pore pressure has basically already all dissipated, right? We already know from Terzagh's 1D consolidation solution, it actually takes an infinite amount of time for all of the pore pressure to dissipate, but we get to a point where there's basically no more pore pressure. Well, after that happens, the soil continues settling. So we're talking about this part of the curve right there that's following the mouse cursor. And that settlement follows a slope of C alpha. Well, it's not settlement, it's void ratio versus logarithm of time. And a lot of people have observed that there's basically this linear decrease of void ratio as the logarithm of time increases, and the slope is C alpha. All right, that region of behavior is definitely secondary compression. That's something that everybody agrees upon, that this behavior is for sure secondary compression. Where things get to be a little bit more challenging is in this region here, when primary consolidation is happening. Does secondary compression happen at the same time? Or are those really distinct regions in time that are separated by this time at the end of primary consolidation, T sub P? So, okay, so everybody agrees that settlement that occurs after TP is called secondary compression. So if you call this the secondary compression region, you're definitely going to be correct. But there are differences in the definition. So let's talk about these two different rates. So instead of naming them right now, I'm just going to leave them in equation form. They're both partial derivatives. One is the change in void ratio over the change in effective stress at a constant time. So that little vertical bar just means that time is being held constant. And at that time, we're looking at the rate of change of void ratio with respect to effective stress. So that would be like what we think of as the soil compressibility, right? How much is the void ratio changing as the effective stress changes? Okay, the other rate is the partial derivative of void ratio with respect to time at a constant effective stress. So that's what's happening here, right? When we reach the secondary compression region, the void ratio is continuing to decrease, but the effective stress is staying constant. Now, the overall rate of void ratio change involves contributions from both of these components. It's equal to dE d sigma v prime at a constant t times d sigma v prime dt plus dE dt at a constant sigma v prime. So both of those components are adding together to give you the total amount of void ratio change during primary consolidation and then during secondary compression also. It's just that eventually this d sigma v prime dt goes to zero, so we're only left with this term. There's wide agreement that both of these components are occurring during primary consolidation. Okay, so the primary consolidation phase here is the sum total of the dE d sigma v prime term and the dE dt terms together. All right, now let's go to our first definition of secondary compression. So acknowledging that we have both of these contributions happening all the time, right, we go to definition one, which is that secondary compression is the change in void ratio that occurs after TP. Primary consolidation is the part that occurs before TP. So this is very much a time-driven definition. We're going to find this value TP where the curve kind of changes direction and there's a kink in it there, you know, and you can use the horizontal extension of the flat line part here and maybe a horizontal extension that goes through the inflection point of the curve somewhere near the middle, and TP lies right at the middle, at the intersection of those two lines. What most people say is this is the secondary compression region and this is the primary consolidation region. Okay, now this is the traditional definition. You probably can find a figure that looks just like this in the Holtz, Kovacs, and Sheehan textbook in chapter 9. What this implies is that the primary consolidation part consists of both dE d sigma v prime at t and dE dt sigma v prime, whereas secondary compression is only dE dt at constant sigma v prime, right? Assuming that, the d sigma v prime dt goes to 0 at that time. All right, and according to this definition, primary consolidation and secondary compression do not occur at the same time, simply because that's how we're defining them, right? Secondary compression happens after TP, primary consolidation happens before TP, so they can't happen at the same time. This definition is a little bit unsatisfactory to me, because we still are getting this EDT at constant sigma v prime happening before TP. So from a mechanistic perspective, whatever is causing secondary compression to happen is also happening during primary consolidation. You could also think of it this way. Imagine that we've gone through some loading sequence and we've clearly reached what everybody would agree is the secondary compression region of the soil. Then what if we were to load it again and go through another consolidation episode? Are we saying that secondary compression would then stop and it would become primary consolidation until we reach a new TP, and then it would become secondary compression again? That part's a little bit strange to me too. So I think this definition, although it's really convenient, and we'll see how it can be used to estimate settlement time histories for real sites that have secondary compression, some funny things about it. All right, so let's look at definition 2. In this case, primary consolidation is defined as the mechanism, right? So it's this ratio, dE d sigma v prime at constant time. So let's just say that is primary consolidation. We're going to divvy this up now, not based on time, but on contribution. And secondary compression is dE dt at constant sigma v prime. Now in this case, the part that occurs before the end of primary consolidation is actually a mix of primary consolidation and secondary compression, because both of these components act at the same time. On the other hand, once the d sigma v prime dt term goes to 0, we're only left with the dE dt term at constant sigma v prime, so you only have secondary compression happening here. When I think of secondary compression, this is the definition that I think of, and this is kind of at odds with probably the more traditional definition, actually, in geotechnical engineering. So regardless of which definition you use, it's just important to be clear on what you mean, right? So when you define secondary compression, be clear about what it is that you're talking about. According to this definition that I prefer, primary consolidation and secondary compression can occur at the same time. So when you have this loading sequence and then you add another loading sequence, the secondary compression that was occurring just continues to occur. Maybe it changes a little bit as a result of stress changes or something like that, but it doesn't stop suddenly and then resume when you reach TP again. So I think that definition has a little bit more rigor when it comes to the actual mechanisms that are controlling the soil behavior. All right, once again, regardless of how we define it, everybody agrees that d sigma v prime at constant time and d sigma v prime dt at constant sigma v prime both occur at the same time during primary consolidation. So it's kind of a funny semantic thing that we're dealing with here. But some people just say the combination of these two is secondary compression, whereas I say this one alone, d sigma v prime dt at sigma v prime constant, is secondary compression. Anyway, just be clear about what you mean when you talk about it. All right, let's talk now about this coefficient of secondary compression, C alpha. So in the figure up here, remember C alpha is the slope. It's dE over d log t. And usually we measure it in the part of the curve where there's no more primary consolidation, because we want to just measure the secondary compression part. We don't want to measure a mix of both. All right, and so C alpha, here's the fundamental definition, dE over d log sigma t, measured after primary consolidation. There's another useful parameter that we'll use when we start estimating settlement due to secondary compression, where instead of having a C alpha, which is a change in void ratio over change in log time, we convert it to a C alpha epsilon, which is a change in vertical strain or change in volumetric strain over change in log time. When we go to settlement, what we really care about is strain. We want to integrate the strain over the layer height, and that's equal to the settlement. So in going from a strain to a void ratio, we divide by 1 plus E naught. All right, that just comes out of phase relationships. We get right here, epsilon V is equal to delta E over 1 plus E, right? So I guess we can have the change in volumetric strain, it's change in void ratio over 1 plus E. So all we're doing is making a substitution here, and we end up with the 1 plus E naught if we make a substitution for delta E up there. So in defining C alpha epsilon, we get this equation. Now the best way to get C alpha is to do a consolidation test, get a curve that looks like this one, right, that where you clearly have a linear part of the secondary compression slope after primary consolidation, and just directly measure C alpha. That's the best way to do it. It may vary with different load stages, and you may have to select the load stage that most closely matches your field loading condition, but if you measure C alpha, that's the best. There are some empirical relationships, though. Mesri and Godlewski, 1977, developed an important concept that C alpha is linearly proportional to C sub C. C sub C is the virgin compression index. And they found that C alpha over C sub C was equal to 0.01 to 0.07, right? Just a constant number. With the 0.01 really being for inorganic materials that are generally probably lower plasticity, and 0.07 being like a peat, right? Very high organic content soil. So organic soils tend to have a higher C alpha over CC. They also tend to have a higher C sub C too, so the C alpha can be really much higher for an organic soil because CC is bigger and C alpha over CC is bigger. But again, better to measure C alpha for your particular test. If you do a consolidation test, you should use it. Don't use a relationship like this. If you really just don't have data or can't reasonably get data on C alpha, then you can use this sort of C alpha over CC assumption, and you'll probably be okay doing that.